Close your eyes for a moment and picture this. You're floating in the endless expanse of space, surrounded by an infinite sea of stars, galaxies, and cosmic wonders. But there's something else here, something faint yet profound, a gentle glow that permeates every corner of the universe. This isn't just any light. It's the oldest light in existence, a whisper from the very beginning of time itself. This is the cosmic background radiation, a relic of the Big Bang, and it holds secrets that can unlock the story of our universe. Think about it. Everywhere you look, every direction you turn, this ancient light is there, a silent witness to the birth of everything we know. It's like a cosmic fingerprint, imprinted on the fabric of space and time. But what does it mean? How did it come to be? And what can it tell us about the universe's earliest moments? By the end of this journey, you'll not only understand the mysteries of this cosmic glow, but also see how it connects us to the very origins of existence. So, where are you joining us from, and what time is it there? Let's dive into this cosmic story together as we explore the secrets of the cosmic background radiation, a light that has traveled across billions of years to reach us, carrying the story of the universe itself. Now, let's take a step back in time, way back, to the very beginning. The Big Bang Theory is the cornerstone of our understanding of how the universe came to be. It's not just a theory about an explosion, as the name might suggest. Instead, it's the story of how everything, space, time, matter, and energy, began from an unimaginably hot and dense point, smaller than a single atom. Imagine this. Around 13.8 billion years ago, the universe was a tiny, infinitely dense speck. In a fraction of a second, it expanded rapidly, cooling as it grew. This wasn't an explosion into space, but rather the expansion of space itself. As the universe stretched, it cooled enough for particles to form, eventually giving rise to atoms, stars, galaxies, and everything we see today. This incredible event didn't just create the universe as we know it, it also set the stage for the cosmic background radiation. As the universe expanded and cooled, it reached a point where light could finally travel freely. That light, released when the universe was just a baby, is what we now detect as the cosmic background radiation. It's like a snapshot of the universe's earliest moments, frozen in time and still visible today. So, when we talk about the Big Bang, we're not just talking about the birth of the universe. We're talking about the origin of everything, the foundation upon which the cosmic background radiation was built. And as we'll see, this ancient light holds the key to understanding not just where we came from, but how the universe itself evolved over billions of years. Now, let's fast forward billions of years from the Big Bang to a moment that changed our understanding of the universe forever. In 1965, two scientists, Arno Penzias and Robert Wilson, made a discovery that would earn them a Nobel Prize and reshape cosmology. But here's the twist. They weren't even looking for it. Penzias and Wilson were working at Bell Labs in New Jersey, using a large radio antenna to study signals from space. But no matter where they pointed the antenna, they kept picking up a faint, persistent noise. At first, they thought it was interference, maybe from nearby cities, or even pigeon droppings on the antenna. They cleaned the equipment, checked for every possible source of error, but the noise wouldn't go away. What they didn't realize at the time was that this mysterious signal wasn't a mistake. It was the faint echo of the Big Bang itself, the cosmic background radiation. This radiation, predicted by theorists years earlier, was the leftover heat from the universe's birth. It was everywhere, filling the cosmos like a whisper from the past. When Penzias and Wilson finally connected the dots, their discovery became one of the most important in modern science. It provided the first direct evidence for the Big Bang theory, confirming that the universe had a beginning. Their accidental find didn't just solve a scientific mystery, it opened the door to a deeper understanding of the cosmos. This discovery also highlighted the challenges of scientific exploration. Sometimes, the answers we're looking for come in ways we least expect. For Penzias and Wilson, it wasn't about chasing a grand theory. It was about paying attention to the details, even when they seemed like nothing more than a nuisance. And in doing so, they gave us a glimpse into the universe's earliest moments, a story written in light that had been traveling for billions of years. As we'll see next, this ancient light isn't just a relic of the past, it's a map, revealing the structure and history of the universe in ways we're still uncovering today. So, what exactly is this cosmic background radiation? Imagine the universe as a newborn, just moments after its birth. In those early stages, it was unimaginably hot and dense, filled with a searing glow of energy. But as the universe expanded and cooled, that intense light began to fade, stretching and shifting over billions of years. What we see today as cosmic background radiation is the faint, lingering echo of that ancient light, a cosmic whisper from the very beginning of time. Think of it like this: if the Big Bang was the universe's first flash of light, the cosmic background radiation is the dim afterglow that's still visible, even after all this time. It's the oldest light in existence, traveling across the cosmos for nearly 14 billion years to reach us. And here's the fascinating part: it's everywhere. No matter where you look in the sky, this faint radiation fills the void, a universal fingerprint of the Big Bang itself. But why is it so important? This radiation isn't just a relic of the past, it's a treasure trove of information. By studying it, scientists can piece together the story of how the universe evolved, from its fiery beginnings to the vast, structured cosmos we see today. It's like having a time machine that lets us peer back to the universe's earliest moments, revealing secrets about its birth, growth, and even its ultimate fate. Now, you might wonder why we can't see this radiation with our eyes. That's because it's no longer visible light. Over billions of years, the expansion of the universe has stretched its wavelength, shifting it into the microwave part of the spectrum. To us, it's invisible, but with the right tools, like the instruments used by Penzias and Wilson, we can detect it and unlock its mysteries. As we'll explore next, this ancient light isn't just a static snapshot of the past. It's a dynamic map, filled with tiny ripples and patterns that tell us even more about the universe's structure and history. These subtle variations hold the key to understanding how galaxies, stars, and even planets came to be. So, while the cosmic background radiation might seem like a faint whisper, it's actually one of the loudest voices in the story of our universe. Now, let's take a step back in time, way back, to when the universe was just a fraction of a second old. Picture it as a blazing, chaotic soup of energy, so hot and dense that light couldn't even travel freely. Photons, the particles of light, were constantly colliding with electrons, trapped in a cosmic dance of heat and pressure. But then, something extraordinary happened. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine, forming the first atoms. This moment, known as recombination, marked a turning point. For the first time, light could travel unimpeded. The universe, once opaque and glowing, became transparent. This newly freed light is what we now call the cosmic background radiation, the universe's first light. It's like the moment a fog lifts, revealing a clear sky. But instead of a sky, it was the entire cosmos, glowing with the light of its birth. This light wasn't just a flash in the pan. It carried with it the imprint of the universe's earliest moments, a snapshot of its temperature, density, and structure. As the universe continued to expand, this light stretched and cooled, shifting from visible wavelengths to the microwave spectrum we detect today. Yet, even in its faint, stretched form, it remains a powerful messenger from the past. What's truly remarkable is how this light connects us to the universe's infancy. It's not just a relic, it's a living record of the cosmos's first breath. By studying it, we can trace the universe's journey from a searing, dense fireball to the vast, structured expanse we see today. And as we'll see next, this light isn't uniform. It's filled with tiny ripples that hold the secrets to the universe's growth and evolution. So, while the cosmic background radiation might seem like a distant echo, it's actually a vibrant chapter in the story of everything. Now, let's zoom in on the cosmic microwave background, or CMB, and uncover why it's such a fascinating piece of the cosmic puzzle. This ancient light, born from the universe's first moments, has traveled across billions of years to reach us. But here's the catch. It's not the kind of light we can see with our eyes. Instead, it exists in the microwave part of the electromagnetic spectrum. To understand why, think about how the universe has expanded over time. When the CMB was first emitted, it was incredibly hot and energetic, glowing with visible light. But as the universe stretched and cooled, so did this light. The wavelengths of the photons stretched along with the fabric of space itself, shifting from visible light to longer, cooler wavelengths. Today, these wavelengths fall into the microwave range, which is why we call it the cosmic microwave background. Microwaves are a type of electromagnetic radiation, just like visible light, but they have much longer wavelengths, about the size of a grain of rice compared to the tiny wavelengths of visible light. This makes them invisible to our eyes, but not to our instruments. Specialized telescopes, like those used in the COBE and Planck missions, are designed to detect these faint microwave signals, allowing us to map the CMB in incredible detail. So, why does this matter? The microwave nature of the CMB is a direct consequence of the universe's expansion. It's like a cosmic fingerprint, preserving the conditions of the early universe in a form we can study. And while we can't see it with our eyes, The CMB is everywhere, filling the entire cosmos with a faint glow that tells the story of how everything began. As we'll explore next, this glow isn't perfectly smooth. It's filled with tiny ripples and variations, each one a clue to the universe's structure and evolution. But for now, just imagine this. Every time you heat up a meal in a microwave, you're using the same kind of energy that carries the oldest light in the universe. It's a humbling reminder of how deeply connected we are to the cosmos. Now, let's take a closer look at one of the most groundbreaking missions in the history of cosmology, the Cosmic Background Explorer, or COBE. Launched in 1989, COBE was designed with one primary goal: to study the cosmic microwave background with unprecedented precision. This mission marked a turning point in our understanding of the universe, providing the first detailed map of the CMB and confirming predictions made by the Big Bang theory. The COBE mission was equipped with 3 specialized instruments, each playing a crucial role in unraveling the mysteries of the CMB. The first, called the differential microwave radiometer, measured tiny temperature differences in the CMB across the sky. These variations, though incredibly small, just a fraction of a degree, were vital clues about the early universe's structure. The second instrument, the far-infrared absolute spectrophotometer, studied the spectrum of the CMB, confirming its blackbody nature and aligning perfectly with the predictions of the Big Bang. Finally, the diffuse infrared background experiment explored the infrared background, shedding light on the formation of the first stars and galaxies. What made COBE so revolutionary was its ability to detect the faintest ripples in the CMB. These ripples, often referred to as anisotropies, are like cosmic fingerprints, tiny imprints left over from the universe's infancy. They reveal the seeds of all the structures we see today, from galaxies to galaxy clusters. By mapping these fluctuations, COBE provided the first direct evidence that the early universe was not perfectly smooth, but had slight variations in density. These variations acted as the building blocks for everything that followed. The results from COBE were nothing short of extraordinary. The mission's findings not only confirmed the Big Bang theory, but also gave us a glimpse into the universe's earliest moments. For their groundbreaking work, the COBE team, led by John Mather and George Smoot, was awarded the Nobel Prize in Physics in 2006. Their discoveries laid the foundation for future missions like WMAP and Planck, which would refine our understanding of the CMB even further. As we reflect on the COBE mission, it's worth noting how it transformed our view of the cosmos. Before COBE, the CMB was a theoretical prediction. After COBE, it became a tangible map, a snapshot of the universe, as it was just 380,000 years after the Big Bang. This mission didn't just confirm a theory, it opened a new window into the past, allowing us to peer back in time and witness the universe's first light. Next, we'll explore how these tiny ripples in the CMB hold the key to understanding the universe's large-scale structure and evolution. But for now, let's appreciate the monumental achievement of COBE, a mission that brought the echoes of the Big Bang into sharp focus and forever changed our understanding of the cosmos. Now, let's zoom in on those tiny ripples in the cosmic microwave background, the faint whispers of the universe's infancy. These fluctuations, though incredibly subtle, hold the key to understanding how the cosmos evolved from a hot, dense soup of particles into the vast, intricate web of galaxies and clusters we see today. Imagine these ripples as the universe's first brushstrokes, painting the blueprint for everything that would come after. These variations in temperature and density, detected by missions like COBE, are no larger than 1 part in 100,000. To put it simply, if the CMB were a smooth ocean, these ripples would be the tiniest waves, barely noticeable, yet profoundly significant. They represent the slight unevenness in the early universe, regions where matter was just a little denser or a little sparser than average. Over billions of years, gravity amplified these differences, pulling matter together into the first stars, galaxies, and eventually, the large-scale structures we observe today. Think of it like planting seeds in a garden. The ripples in the CMB are the seeds, and the universe is the soil. Where the seeds are slightly denser, galaxies grow. Where they're sparser, vast cosmic voids form. These fluctuations are the universe's way of setting the stage for its own evolution, creating the scaffolding upon which all cosmic structures are built. What's truly remarkable is how these ripples connect the past to the present. By studying their patterns, scientists can trace the history of the universe, understanding how it expanded, cooled, and gave rise to the complexity we see today. These tiny imprints are like a cosmic time capsule, preserving the conditions of the universe just 380,000 years after the Big Bang. As we continue to map these ripples with ever greater precision, we uncover more about the forces that shape the cosmos. From the pull of dark matter to the push of dark energy, these fluctuations tell a story that spans billions of years. They remind us that even the smallest details can have the most profound consequences, shaping the universe on the grandest scales. Next, we'll explore how missions like Planck have taken this exploration even further, refining our understanding of these cosmic ripples and revealing new layers of the universe's history. But for now, let's marvel at the fact that these tiny fluctuations, so small, they're almost imperceptible, are the very foundation of everything we see in the night sky. Building on the foundation laid by earlier missions, the Planck satellite took our exploration of the cosmic microwave background to extraordinary new heights. Launched in 2009 by the European Space Agency, Planck was designed to observe the universe with unparalleled sensitivity and precision. Its advanced instruments allowed it to measure the temperature and polarization of the CMB with a level of detail never before achieved, offering us a sharper, more refined picture of the universe's earliest moments. What set Planck apart was its ability to detect even the faintest variations in the CMB, down to a few millionths of a degree. To put this into perspective, imagine trying to measure the temperature of a cup of coffee from across the room, but with such precision that you could detect the tiniest fluctuations caused by a single grain of sugar dissolving. That's the kind of accuracy Planck brought to the study of the universe's first light. One of Planck's most groundbreaking achievements was its detailed map of the CMB, which revealed the subtle patterns of temperature and density fluctuations with incredible clarity. These patterns are like fingerprints, unique to the early universe, and they hold clues about the conditions that existed just moments after the Big Bang. By analyzing these patterns, scientists were able to confirm key predictions of the Big Bang theory, such as the universe's overall flatness and the precise proportions of ordinary matter, and dark energy. But Planck didn't stop there. It also provided new insights into the universe's age and expansion rate. By refining measurements of the CMB, Planck helped pin down the age of the universe to an astonishingly precise 13.8 billion years, with a margin of error of just a few tens of millions of years. This level of accuracy is like measuring the distance from Earth to the Moon down to the width of a single hair. Perhaps most intriguingly, Planck's data also shed light on the mysterious forces shaping the cosmos. Its observations of the CMB's polarization patterns offered tantalizing hints about the role of dark energy in driving the universe's accelerating expansion. While many questions remain, Planck's findings have brought us closer than ever to understanding the fundamental forces that govern the cosmos. As we reflect on Planck's contributions, it's clear that this mission has not only deepened our understanding of the CMB, but also reshaped our view of the universe itself. Its legacy continues to inspire new questions and guide future missions, ensuring that the story of the cosmic microwave background and the universe it reveals remains as vibrant and dynamic as ever. Next, we'll explore how these tiny ripples in the CMB might hold clues to even grander mysteries, including the possibility of other universes beyond our own. Now, let's take a step back and think of the cosmic background radiation as something truly extraordinary, a snapshot of the universe in its infancy. Imagine holding a photograph of yourself as a baby, one that captures the very first moments of your existence. Just as that photo reveals your earliest features, the cosmic background radiation offers us a glimpse of the universe when it was just a newborn, only about 380,000 years old. This ancient light is like a time capsule, preserving the conditions of the cosmos at a time when it was far simpler, hotter, and denser than it is today. This baby picture of the universe shows us a time before stars, galaxies, or planets had formed. Back then, the universe was a swirling sea of particles and energy, still cooling from the explosive birth of the Big Bang. As the universe expanded and cooled, it reached a point where light could finally travel freely, creating the first glow that we now detect as the cosmic background radiation. This glow is the oldest light we can observe, and it carries with it the imprints of the universe's earliest moments. What makes this baby picture so remarkable is how much it tells us about the universe's growth and evolution. Just as a child's early photos can hint at their future traits, the patterns in the cosmic background radiation reveal the seeds of the structures we see today. Those tiny fluctuations in temperature and density, which Planck and other missions have mapped with such precision, are the building blocks of everything around us. Over billions of years, these small ripples grew into the vast cosmic web of galaxies, clusters, and voids that define our universe. But this baby picture isn't just a static image, it's a dynamic record of change. By studying it, we can trace the universe's journey from its fiery beginnings to the complex, beautiful cosmos we inhabit today. It's like watching a time-lapse video of a child growing up, except this one spans nearly 14 billion years. And just as a family photo album helps us understand our own history, the cosmic background radiation helps us piece together the story of the universe itself. As we marvel at this ancient snapshot, it's worth reflecting on how far we've come in understanding it. From its accidental discovery in the 1960s to the groundbreaking maps created by missions like Planck, the cosmic background radiation has transformed our view of the cosmos. It's a reminder that even the faintest whispers of light can carry profound truths about our origins and our place in the universe. Next, we'll explore how this baby picture has helped scientists determine the age of the universe, unlocking yet another piece of the cosmic puzzle. Now, let's turn our attention to one of the most fascinating discoveries made possible by the cosmic background radiation: the age of the universe itself. This ancient light doesn't just show us what the universe looked like in its infancy. It also acts as a cosmic clock, helping scientists calculate how long it has been since the Big Bang. By carefully analyzing the patterns and properties of this radiation, researchers have been able to pinpoint the universe's age with remarkable precision. The current estimate, 13.8 billion years. To understand how this works, think of the cosmic background radiation as a kind of fossilized echo from the early universe. Just as archaeologists use fossils to date ancient life, cosmologists use this radiation to trace the timeline of the cosmos. The key lies in the temperature and distribution of the radiation. As the universe expanded and cooled over billions of years, the light from the cosmic background radiation stretched and shifted into the microwave range. By measuring this shift and comparing it to theoretical models, scientists can determine how much time has passed since the universe began. One of the most important tools in this process is the Planck satellite, which mapped the cosmic background radiation with unprecedented detail. By studying the tiny fluctuations in temperature and density within this radiation, Planck provided data that allowed scientists to refine their calculations. These fluctuations are like cosmic breadcrumbs, leading us back to the moment when the universe transitioned from a hot, dense state to the cooler, more structured cosmos we see today. The precision of these measurements is astounding, narrowing down the universe's age to within just a few million years of accuracy. But why does this matter? Knowing the age of the universe isn't just a number, it's a cornerstone of our understanding of cosmology. It helps us piece together the timeline of cosmic events, from the formation of the first atoms to the birth of stars and galaxies. It also provides a framework for testing other theories about the universe's composition, expansion, and ultimate fate. Without the cosmic background radiation, we wouldn't have this crucial piece of the puzzle. As we reflect on this discovery, it's worth marveling at how far we've come. Just a century ago, the idea of measuring the age of the universe seemed like science fiction. Today, thanks to the faint glow of the cosmic background radiation, we can confidently say that the universe is 13.8 billion years old. This number isn't just a statistic, it's a testament to the power of human curiosity and ingenuity. Next, we'll explore how this ancient light also reveals the composition of the universe, shedding light on the mysterious ingredients that make up everything we see. Now, let's take a closer look at what the cosmic background radiation tells us about the ingredients that make up the universe. This ancient light isn't just a snapshot of the cosmos in its early stages. It's also a detailed recipe, revealing the precise proportions of ordinary matter, and dark energy that shape everything we see. Ordinary matter, the stuff that makes up stars, planets, and even us, accounts for only about 5% of the universe's total content. It's the part of the universe we can see and interact with, but it's just the tip of the cosmic iceberg. The cosmic background radiation helps us measure this small fraction by analyzing how matter interacts with light, leaving subtle imprints in the radiation's patterns. Then there's dark matter, which makes up roughly 27% of the universe. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it invisible to our telescopes. But its presence is undeniable. The cosmic background radiation shows us how dark matter's gravitational pull influences the distribution of ordinary matter, creating ripples and clumps that eventually formed galaxies and galaxy clusters. Without dark matter, the universe as we know it simply wouldn't exist. Finally, there's dark energy, the most mysterious component of all. It makes up about 68% of the universe and is responsible for its accelerating expansion. The cosmic background radiation provides critical clues about dark energy by revealing how the universe has stretched and evolved over time. By studying the radiation's large-scale patterns, scientists can infer the presence of this enigmatic force, even though we still don't fully understand what it is. Together, these three components, ordinary matter, and dark energy, paint a complete picture of the universe's composition. The cosmic background radiation acts like a cosmic scale, weighing each ingredient and showing us how they interact to shape the cosmos. It's a reminder that what we see is only a small part of the story, and that the universe is far more complex and mysterious than we once imagined. As we continue to explore the secrets of the cosmic background radiation, we'll delve deeper into the role of dark matter and how its invisible presence shapes the universe in ways we're only beginning to understand. Now, let's turn our attention to the invisible force that holds the universe together, dark matter. While we can't see it directly, its influence is written all over the cosmic background radiation. This mysterious substance doesn't interact with light, but its gravitational pull leaves a clear fingerprint on the radiation's patterns, helping us piece together its role in the cosmos. The cosmic background radiation acts like a cosmic detective, revealing how dark matter shaped the early universe. As the universe expanded and cooled after the Big Bang, tiny fluctuations in density began to form. These fluctuations were like seeds, and dark matter's gravity helped them grow. Over billions of years, these seeds became the galaxies and galaxy clusters we see today. Without dark matter, the universe would lack the structure we observe. It's the scaffolding that holds everything together. But how do we know dark matter exists if we can't see it? The answer lies in the subtle distortions in the cosmic background radiation. Dark matter's gravitational pull bends the path of light, creating slight variations in the radiation's temperature and intensity. These variations, though incredibly small, are like cosmic breadcrumbs, leading us to the presence of dark matter. By mapping these distortions, scientists can trace where dark matter is concentrated and how it influences the universe's large-scale structure. What's even more fascinating is that dark matter doesn't just shape the universe, it also helps us understand its evolution. The patterns in the cosmic background radiation show us how dark matter's gravity slowed the expansion of the universe in its early stages, allowing galaxies to form. Later, as dark energy began to dominate, the universe's expansion started to accelerate. This delicate balance between dark matter and dark energy is written in the cosmic background radiation, offering us a glimpse into the forces that have shaped the cosmos over billions of years. As we continue to study the cosmic background radiation, we're uncovering more about dark matter's role in the universe. It's a reminder that even the things we can't see have a profound impact on the world around us. Next, we'll explore how dark energy, the universe's most mysterious force, interacts with the cosmic background radiation to drive the cosmos's accelerating expansion. Now, let's shift our focus to another cosmic mystery, dark energy. While dark matter shapes the universe's structure, dark energy is the force driving its accelerating expansion. The cosmic background radiation holds crucial clues about this enigmatic energy, helping us understand how it influences the fate of the cosmos. When scientists first observed the cosmic background radiation, they noticed something unexpected. The radiation's patterns suggested that the universe wasn't just expanding, it was doing so at an ever-increasing rate. This discovery was groundbreaking, as it contradicted the long-held belief that gravity would eventually slow down the universe's expansion. Instead, something was counteracting gravity's pull, pushing galaxies apart faster and faster. That something is dark energy. But how does the cosmic background radiation reveal dark energy's presence? The answer lies in the radiation's temperature fluctuations. These tiny variations act like a cosmic ruler, allowing scientists to measure distances across the universe. By comparing these measurements with the brightness of distant supernova, researchers found that the universe's expansion is speeding up. This acceleration points directly to the influence of dark energy, which makes up about 68% of the universe's total energy content. What's truly fascinating is how dark energy interacts with the cosmic background radiation. In the early universe, dark matter's gravity dominated, slowing the expansion and allowing galaxies to form. But as the universe grew larger and more diffuse, dark energy began to take over. Its repulsive force started to outweigh gravity's pull, causing the expansion to accelerate. This transition is imprinted in the cosmic background radiation, offering us a timeline of the universe's evolution. The cosmic background radiation also helps us understand the nature of dark energy itself. One leading theory suggests that dark energy is a property of space itself, often referred to as the cosmological constant. This idea, first proposed by Albert Einstein, suggests that empty space has an inherent energy that drives expansion. The patterns in the cosmic background radiation align closely with this theory, providing strong evidence for its validity. As we continue to study the cosmic background radiation, we're uncovering more about dark energy's role in shaping the universe. It's a reminder that the cosmos is filled with forces we're only beginning to understand. Next, we'll explore the horizon problem, a puzzling aspect of the universe's structure, and how the cosmic background radiation helps us solve it. Now, let's turn our attention to one of the most intriguing puzzles in cosmology, the horizon problem. Imagine looking at the night sky and noticing that no matter which direction you gaze, the stars and galaxies seem to be evenly spread out. This uniformity is not just a coincidence, it's a fundamental feature of our universe. But here's the mystery. Regions of the universe that are far apart, even billions of light years away, appear to have the same temperature and density. How is this possible if these regions were never in contact with each other? This is the essence of the horizon problem. To understand why this is puzzling, let's think about how the universe has expanded over time. In the early moments after the Big Bang, the universe was incredibly hot and dense. As it expanded, light and heat began to spread out. However, according to the speed of light, there hasn't been enough time since the Big Bang for these distant regions to exchange heat or information. So, how did they end up so similar? It's like two people on opposite sides of the world, wearing the exact same outfit without ever having met or communicated. This is the horizon problem in a nutshell. This is where the cosmic background radiation comes into play. When we observe the radiation, we see that it is remarkably uniform across the sky, with only tiny fluctuations. This uniformity suggests that the entire universe was once in close contact, allowing it to reach a state of equilibrium. But how could this have happened if the universe expanded so rapidly? The answer lies in a theory called cosmic inflation. Cosmic inflation proposes that in the earliest moments of the universe, it underwent an incredibly rapid expansion, faster than the speed of light. This brief but explosive growth stretched the universe from a tiny, uniform region to the vast cosmos we see today. During this period, regions that were once close together were suddenly pushed far apart, but they retained their uniformity because they had already been in thermal equilibrium. This explains why the cosmic background radiation looks so similar in all directions, even though the regions it represents are now separated by immense distances. The theory of cosmic inflation not only solves the horizon problem, but also provides a framework for understanding the large-scale structure of the universe. The tiny fluctuations we see in the cosmic background radiation are the seeds of galaxies and galaxy clusters planted during this rapid expansion. Without inflation, it's hard to imagine how the universe could have become so uniform on such a grand scale. As we continue to study the cosmic background radiation, we gain deeper insights into the early universe and the forces that shaped it. The horizon problem, once a baffling mystery, now serves as a key piece of evidence supporting the theory of cosmic inflation. Next, we'll dive deeper into this theory, exploring how it explains not only the uniformity of the universe, but also the intricate patterns we observe in the cosmic background radiation. Now, let's take a closer look at the theory of cosmic inflation and how it ties into the cosmic background radiation. Picture the universe in its earliest moments, smaller than a single atom, yet filled with unimaginable energy. Cosmic inflation suggests that in a fraction of a second, this tiny speck underwent an exponential expansion, growing faster than the speed of light. This rapid stretching didn't just make the universe bigger, it also smoothed out any irregularities, creating the uniformity we see in the cosmic background radiation today. Think of it like blowing up a balloon. If you draw tiny dots on the surface before inflating it, those dots will spread apart as the balloon expands. In the same way, the universe's rapid growth during inflation stretched out any initial variations, leaving behind a nearly uniform canvas. This explains why the cosmic background radiation appears so evenly distributed across the sky, even though the regions it represents are now billions of light years apart. But inflation didn't just create uniformity, it also planted the seeds for the universe's structure. During this rapid expansion, tiny quantum fluctuations were magnified, creating slight variations in density. These fluctuations, though incredibly small, became the building blocks for everything we see today. The slightly denser regions eventually collapsed under gravity, forming galaxies, stars, and even the vast cosmic web that connects the universe. When we look at the cosmic background radiation, those faint ripples are the fingerprints of these early fluctuations, frozen in time. The theory of cosmic inflation also helps us understand why the universe is so flat on large scales. Just as inflating a balloon makes its surface appear flatter, the rapid expansion of the universe smoothed out any curvature, leaving it with the geometry we observe today. This flatness is another key prediction of inflation, supported by precise measurements of the cosmic background radiation. As we piece together the story of cosmic inflation, it's remarkable how well it aligns with what we observe in the cosmic background radiation. The uniformity, the tiny fluctuations, and the flat geometry all point to a universe that underwent a brief but transformative growth spurt in its infancy. This theory not only solves the horizon problem, but also provides a framework for understanding how the universe evolved from a hot, dense state to the complex, structured cosmos we inhabit today. Next, we'll explore another fascinating aspect of the cosmic background radiation, the search for a unique signature called B-mode polarization, which could reveal even more about the universe's earliest moments. Now, let's turn our attention to a fascinating and elusive feature hidden within the cosmic background radiation, B-mode polarization. This subtle pattern, if detected, could provide a direct glimpse into the universe's earliest moments, offering clues about the gravitational waves that rippled through space during cosmic inflation. Imagine these gravitational waves as tiny ripples on the surface of a pond, but instead of water, they're distortions in the fabric of spacetime itself. These ripples, generated by the violent expansion of the universe, would have left their mark on the cosmic background radiation, imprinting a unique swirl-like pattern known as B-mode polarization. To understand B-mode polarization, let's first break down what polarization means. Light, including the cosmic background radiation, can be thought of as waves that vibrate in specific directions. When this light interacts with matter or is influenced by gravitational waves, its vibrations can become aligned in particular ways, creating patterns of polarization. B-mode polarization is a specific type of pattern that resembles a swirling or twisting motion, distinct from other forms of polarization. Detecting this signature would be like finding a cosmic fingerprint, revealing the presence of gravitational waves from the universe's infancy. The search for B-mode polarization is one of the most exciting challenges in modern cosmology. Scientists use highly sensitive instruments, like specialized telescopes and detectors, to scan the cosmic background radiation for these faint swirls. The difficulty lies in separating this signal from other sources of polarization, such as dust in our own galaxy or distortions caused by intervening matter. It's like trying to hear a whisper in a crowded room. Every detail matters, and even the smallest interference can obscure the signal. Why is this search so important? If B-mode polarization is confirmed, it would provide strong evidence for the theory of cosmic inflation, supporting the idea that the universe underwent a rapid expansion in its earliest moments. It would also give us a direct window into the energy scales of the early universe, helping us understand the conditions that existed just fractions of a second after the Big Bang. This discovery would be a monumental step forward in our quest to unravel the mysteries of the cosmos. So far, the search has yielded tantalizing hints, but no definitive detection. Experiments like the BICEP and Keck array collaborations have made significant progress, narrowing down the possibilities and refining our techniques. Each new observation brings us closer to uncovering this cosmic signature, pushing the boundaries of what we know about the universe's origins. As we continue to explore the cosmic background radiation, the hunt for B-mode polarization reminds us of the incredible precision and patience required in cosmology. It's a testament to humanity's curiosity and determination to understand the universe's deepest secrets. Next, we'll delve into another intriguing idea: how the cosmic background radiation might hold clues about the existence of other universes, opening the door to the speculative realm of the multiverse. Now, let's venture into one of the most mind-bending ideas in modern cosmology: the multiverse. Could the cosmic background radiation hold clues about other universes beyond our own? This question takes us into the realm of speculative science, where the boundaries of our understanding are pushed to their limits. The multiverse theory suggests that our universe might be just one of countless others, each with its own unique properties and laws of physics. While this idea may sound like science fiction, some scientists believe that the cosmic background radiation could offer subtle hints about the existence of these parallel worlds. One way the cosmic background radiation might reveal evidence of a multiverse is through anomalies or patterns that don't fit our current understanding of the universe. For instance, if we detect unusual temperature fluctuations or unexpected alignments in the radiation, these could be signs of interactions between our universe and others. Imagine the cosmic background radiation as a cosmic canvas. Any unexpected brushstrokes or smudges might indicate that something beyond our universe has left its mark. These anomalies could be the fingerprints of neighboring universes, subtly influencing the fabric of our own. Another intriguing possibility involves the concept of cosmic collisions. In a multiverse scenario, it's possible that other universes could have collided with ours in the distant past. Such collisions might have left imprints in the cosmic background radiation, creating distinctive patterns or distortions. Detecting these signatures would be like finding scars on the surface of space-time, telling the story of a long-ago encounter with another universe. While this idea is still highly speculative, it highlights the potential for the cosmic background radiation to serve as a window into realities beyond our own. The multiverse theory also ties into the concept of cosmic inflation, the rapid expansion of the universe in its earliest moments. Some models of inflation suggest that this expansion could have created bubbles of space, each forming its own universe with different physical properties. If this is true, the cosmic background radiation might carry faint echoes of these bubble universes, offering indirect evidence of their existence. It's like listening to the faint whispers of distant neighbors, each with their own unique story to tell. Of course, the search for evidence of a multiverse is incredibly challenging. The signals we're looking for would be extremely subtle, buried within the noise of the cosmic background radiation. Scientists are developing increasingly sophisticated tools and techniques to sift through this data, searching for any clues that might point to the existence of other universes. While we haven't found definitive proof yet, the very possibility opens up a universe of questions and possibilities, inviting us to rethink our place in the cosmos. As we ponder the idea of a multiverse, it's worth reflecting on what this means for our understanding of reality. If other universes exist, each with its own laws of physics, what does that say about the nature of existence itself? The cosmic background radiation, as a relic of the Big Bang, might hold the key to answering these profound questions. Next, we'll explore how this ancient light helps us understand the shape of the universe, shedding light on its geometry and ultimate fate. Now, let's turn our attention to one of the most fascinating questions in cosmology. What shape does the universe have? The cosmic background radiation plays a crucial role in answering this question, offering clues about the geometry of the cosmos on the grandest scales. Imagine the universe as a vast, cosmic sheet. Is it curved like a sphere, warped like a saddle, or perfectly flat? The answer lies in the patterns etched into the cosmic background radiation. Scientists use the cosmic background radiation to measure the universe's geometry by studying how light from the early universe has traveled across space and time. If the universe were curved, the paths of this ancient light would bend, creating distortions in the radiation's patterns. A spherical universe would cause light to converge, while a saddle-shaped one would make it diverge. But what the cosmic background radiation reveals is something extraordinary. The universe appears to be flat on large scales. This flatness means that parallel lines stay parallel, and the angles of a triangle add up to 180 degrees, just as they do in the geometry we learn in school. This discovery has profound implications. A flat universe suggests that the total amount of matter and energy in the cosmos is finely balanced, a concept known as the critical density. If there were too much matter, the universe would curve inward like a sphere. Too little, and it would curve outward like a saddle. The fact that the universe is flat indicates that this balance is precise, a result that aligns with our understanding of cosmic inflation, the rapid expansion of the universe in its earliest moments. Inflation would have stretched the universe so much that any initial curvature became imperceptible, leaving us with the flat geometry we observe today. But how do we know the universe is flat? The key lies in the tiny temperature fluctuations within the cosmic background radiation. These fluctuations act like a cosmic ruler, allowing scientists to measure the angles of triangles formed by the radiation's patterns. If the universe were curved, these angles would deviate from what we expect in flat space. Yet, the measurements match the predictions for a flat universe with remarkable precision, confirming the geometry of the cosmos on the largest scales. This flatness doesn't just tell us about the shape of the universe, it also provides insights into its composition. A flat universe requires a specific mix of ordinary matter, and dark energy to maintain its geometry. This balance is a cornerstone of modern cosmology, helping us piece together the puzzle of how the universe evolved and what it's made of. As we reflect on the shape of the universe, it's awe-inspiring to think that the cosmic background radiation, a relic of the Big Bang, holds the answers to such profound questions. Next, we'll explore how this ancient light also offers clues about the ultimate fate of the universe, revealing whether it will expand forever or eventually collapse. Now, let's take a step further into the mysteries of the cosmos and explore what the cosmic background radiation tells us about the ultimate fate of the universe. Will it continue to expand forever, or will it one day collapse back in on itself? This question has fascinated scientists and dreamers alike, and the answers lie hidden within the faint glow of the cosmic background radiation. The fate of the universe is deeply tied to its composition and the forces that govern its expansion. As we've seen, the cosmic background radiation reveals a universe that is flat, with a precise balance of matter, and dark energy. But what does this balance mean for the future? To understand this, we need to look at how these components interact over time. Dark energy, the mysterious force driving the accelerated expansion of the universe, plays a starring role in this cosmic drama. If dark energy continues to dominate, the universe will keep expanding at an ever-increasing rate, stretching galaxies farther and farther apart until they are isolated islands in an ever-growing void. This scenario is often called the Big Freeze, where the universe grows cold and dark as stars burn out and galaxies fade into obscurity. But what if dark energy behaves differently over time? Some theories suggest that dark energy could weaken or even reverse its effects. If this happens, gravity might regain the upper hand, pulling the universe back together in a dramatic collapse known as the Big Crunch. In this scenario, the universe would shrink back to a hot, dense state, much like its beginnings, potentially setting the stage for another Big Bang. The cosmic background radiation offers clues about these possibilities by helping scientists measure the rate of expansion and the behavior of dark energy. By studying the patterns and fluctuations in the radiation, researchers can test different models of the universe's future, narrowing down the possibilities. One of the most intriguing aspects of this research is how it connects the past to the future. The cosmic background radiation is a snapshot of the universe's infancy, but it also holds the key to understanding its destiny. The same forces that shaped the early universe, gravity, dark matter, and dark energy, are still at work today, guiding its evolution. By decoding the messages left in this ancient light, we can glimpse not only where we came from, but also where we might be headed. As we ponder the fate of the universe, it's humbling to realize that the answers are written in the faint glow of the cosmic background radiation, a relic of the Big Bang that continues to illuminate the deepest mysteries of existence. Next, we'll delve into the challenges scientists face in measuring this ancient light and the groundbreaking missions that aim to uncover even more secrets from the dawn of time. Measuring the cosmic background radiation is no simple task. It's like trying to listen to a whisper in a crowded room, where every sound around you threatens to drown out the faint signal you're trying to hear. One of the biggest challenges scientists face is interference from Earth's atmosphere. Our atmosphere is filled with water vapor, oxygen, and other molecules that absorb and emit radiation, creating noise that can obscure the delicate signals of the cosmic background radiation. To overcome this, researchers often place their instruments in high-altitude locations, like mountaintops, or even send them into space, where the atmosphere doesn't interfere. But the atmosphere isn't the only source of interference. The universe itself is filled with other sources of radiation that can muddy the waters. For example, our own Milky Way galaxy emits radiation across a wide range of wavelengths, including microwaves. This galactic noise can overlap with the cosmic background radiation, making it harder to isolate the ancient signal. To tackle this, scientists use sophisticated filters and algorithms to separate the cosmic background radiation from these foreground sources, carefully peeling away the layers of interference to reveal the pristine glow of the early universe. Another challenge lies in the precision required to measure the cosmic background radiation. The temperature of this radiation is just a few degrees above absolute zero, and the tiny fluctuations within it are even smaller, on the order of 1 part in 100,000. Detecting these minuscule variations demands incredibly sensitive instruments, often cooled to near absolute zero, to reduce their own thermal noise. Even the slightest imperfection in the equipment or a tiny error in calibration can skew the results, making the process both delicate and demanding. Despite these challenges, scientists have made remarkable progress. Missions like the Cosmic Background Explorer and the Planck satellite have pushed the boundaries of what's possible, providing us with increasingly detailed maps of the cosmic background radiation. Each new mission builds on the lessons of the past, refining techniques and developing new technologies to overcome the obstacles that stand in the way of discovery. As we continue to study this ancient light, we're reminded of the ingenuity and perseverance required to unlock the secrets of the universe. The challenges are immense, but so too are the rewards. Every measurement, every breakthrough, brings us closer to understanding the origins and fate of the cosmos. Next, we'll look at the future missions and technologies that promise to take our exploration of the cosmic background radiation to even greater heights, revealing new insights into the story of our universe. Looking ahead, the quest to uncover the mysteries of the cosmic background radiation is far from over. In fact, the next generation of missions and technologies promises to take our understanding to unprecedented levels. One of the most exciting developments on the horizon is the launch of advanced space telescopes designed to map the cosmic microwave background with even finer detail. These missions aim to capture the faintest whispers of the universe's earliest moments, revealing patterns and fluctuations that could reshape our understanding of cosmic history. One such mission is the Simons Observatory, a ground-based project located in the high-altitude deserts of Chile. This observatory will deploy an array of highly sensitive telescopes, equipped with state-of-the-art detectors capable of measuring the cosmic background radiation with extraordinary precision. By focusing on the polarization of this ancient light, scientists hope to uncover evidence of gravitational waves from the early universe, potentially shedding light on the mysterious period of cosmic inflation. Meanwhile, space-based missions like LightBird, planned by the Japanese Space Agency, are set to take the study of the cosmic background radiation to new heights. LightBird will orbit far from Earth's atmosphere, free from the interference that complicates ground-based observations. Its instruments will scan the sky across multiple frequencies, allowing researchers to separate the cosmic background radiation from other sources of cosmic noise with unparalleled accuracy. This mission could provide the clearest picture yet of the universe's first light, offering insights into the fundamental forces that shape the cosmos. Another groundbreaking project in development is the Cosmic Microwave Background Stage 4 Experiment, or CMBS-4. This ambitious initiative will combine data from multiple telescopes around the world, creating a comprehensive map of the cosmic background radiation with unprecedented resolution. By pooling resources and expertise, scientists aim to detect even the tiniest ripples in this ancient light, which could hold clues about the nature of dark matter, dark energy, and the overall geometry of the universe. These future missions are not just about refining what we already know, they are about opening doors to entirely new discoveries. With each technological leap, we inch closer to answering some of the most profound questions in cosmology. What triggered the Big Bang? What is the true nature of dark energy? Could there be other universes beyond our own? The cosmic background radiation is our window into these mysteries, and the next generation of missions promises to make that window even clearer. As we prepare for these exciting advancements, it's worth reflecting on how far we've come. From the accidental discovery of the cosmic background radiation in the 1960s to the highly detailed maps produced by missions like Planck, our journey to understand the universe's origins has been nothing short of extraordinary. And with the tools and technologies on the horizon, the best may be yet to come. Next, we'll explore how the cosmic background radiation might even hold clues about the existence of advanced alien civilizations and what they could learn from this ancient light. Now, let's take a moment to consider a fascinating possibility. What if we're not the only ones studying the cosmic background radiation? Imagine an advanced alien civilization, perhaps millions or even billions of years ahead of us in technological development. Could they, too, be gazing at this ancient light, unraveling the secrets of the universe just as we are? It's a thought that stretches the imagination, but it's not as far-fetched as it might seem. For any civilization capable of observing the cosmos, the cosmic background radiation would be an irresistible target. After all, it's the oldest light in the universe, a snapshot of the cosmos in its infancy. Advanced alien societies, equipped with technology far beyond our own, might have already mapped the cosmic microwave background with incredible precision, uncovering details that we can only dream of detecting. They could use this ancient light to piece together the history of the universe, just as we do, but with insights that go far beyond our current understanding. One intriguing question is whether these hypothetical civilizations might use the cosmic background radiation to search for other life forms like us. If they've developed the ability to detect subtle patterns or anomalies in this ancient light, they might be able to infer the existence of other intelligent beings. For example, they could analyze the distribution of matter in the early universe, looking for signs of structures that might indicate the presence of life. Or they might study the polarization of the cosmic background radiation to search for evidence of technological activity, such as the remnants of advanced energy systems or even artificial megastructures. But the cosmic background radiation could also serve as a kind of cosmic Rosetta Stone for alien civilizations, just as it helps us understand the fundamental forces and particles that shape the universe. It could provide them with a deeper understanding of physics, perhaps even revealing laws of nature that we haven't yet discovered. For a civilization that has mastered interstellar travel or harnessed the power of stars, the cosmic background radiation might hold the key to unlocking even greater mysteries, such as the nature of dark energy or the possibility of other dimensions. Of course, all of this is speculative. We have no direct evidence that alien civilizations exist, let alone that they are studying the cosmic background radiation. But the idea invites us to think bigger, to consider how the universe might be explored and understood by minds far different from our own. It's a reminder that the cosmic background radiation isn't just a relic of our past. It's a universal treasure, a shared inheritance that connects all potential observers of the cosmos, no matter where or who they are. As we ponder these possibilities, it's worth reflecting on what this means for our own place in the universe. The cosmic background radiation is a bridge between the past and the future, a link that ties us to the earliest moments of existence, and perhaps to other civilizations that might be out there. It's a humbling thought, one that underscores the vastness of the cosmos and the endless potential for discovery. Next, we'll explore how the cosmic background radiation has made its way into popular culture, shaping our imagination and inspiring stories that bring the mysteries of the universe to life. Now, let's shift our gaze from the scientific and speculative to the imaginative and cultural. The cosmic background radiation, while deeply rooted in science, has also found its way into the realm of popular culture, inspiring stories, art, and even philosophical reflections. It's fascinating to see how this ancient light, a relic of the Big Bang, has captured the imagination of creators across various mediums, becoming a symbol of the universe's mysteries and humanity's quest for understanding. In movies and television, the cosmic background radiation often serves as a backdrop for stories that explore the origins of the universe or the nature of existence. For instance, in science fiction films, it's not uncommon to see characters referencing this ancient light as they grapple with questions about the cosmos. The cosmic microwave background becomes a visual and thematic element, representing the vastness of space and the profound questions it raises. It's a reminder that even in fiction, the mysteries of the universe can inspire awe and wonder. Books, too, have embraced the cosmic background radiation as a source of inspiration. Science fiction novels, in particular, often weave it into their narratives, using it as a way to ground fantastical stories in real science. Authors might imagine civilizations that use the cosmic microwave background to communicate across galaxies or to unlock secrets about the universe's earliest moments. These stories not only entertain, but also invite readers to think about the deeper implications of what this ancient light represents. Even in music and art, the cosmic background radiation has left its mark. Composers have created pieces that evoke the eerie, almost otherworldly nature of this ancient light, using soundscapes to capture its cosmic significance. Visual artists, too, have drawn inspiration from the patterns and fluctuations in the cosmic microwave background, creating works that reflect the beauty and complexity of the universe. These artistic interpretations remind us that science and creativity are deeply intertwined, each offering a unique lens through which to view the cosmos. The cultural impact of the cosmic background radiation extends beyond entertainment and art. It has also influenced philosophical and spiritual discussions about the nature of existence and humanity's place in the universe. For some, this ancient light is a symbol of the interconnectedness of all things, a reminder that we are part of a much larger story. It invites us to ponder not just the origins of the universe, but also the meaning of our own lives within it. As we reflect on the cosmic background radiation's presence in popular culture, it's clear that this ancient light is more than just a scientific phenomenon. It's a source of inspiration, a bridge between the known and the unknown, and a testament to humanity's enduring curiosity about the cosmos. Next, we'll delve into the philosophical implications of the cosmic background radiation, exploring how it challenges us to think about the nature of existence and our place in the grand tapestry of the universe. Now, as we turn our attention to the deeper questions that the cosmic background radiation invites us to ponder, we find ourselves stepping into the realm of philosophy. This ancient light, a remnant of the universe's birth, doesn't just tell us about the cosmos, it also challenges us to think about the very nature of existence and our place within it. What does it mean to live in a universe that began with a Big Bang, and how does this knowledge shape our understanding of ourselves? The cosmic background radiation, as the oldest light in the universe, serves as a kind of cosmic mirror. It reflects not only the physical conditions of the early universe, but also the profound questions that have puzzled humanity for centuries. Why is there something rather than nothing? What is the purpose, if any, of the vast expanse of space and time? These are questions that science can describe but not fully answer, and that's where philosophy steps in. The cosmic microwave background becomes a starting point for exploring the boundaries between what we know and what we can only wonder about. One of the most striking philosophical implications of the cosmic background radiation is the idea of our cosmic insignificance, and yet, paradoxically, our profound connection to the universe. When we look at this ancient light, we're seeing a snapshot of the universe when it was just a few 100,000 years old. It's a humbling reminder of how small and fleeting human existence is in the grand timeline of the cosmos. And yet, at the same time, it's a testament to the fact that we are made of the same stuff as the stars and galaxies. We are, in a very real sense, stardust, connected to the universe in ways that are both physical and metaphysical. This duality of being both insignificant and deeply connected raises questions about meaning and purpose. If the universe is so vast and ancient, does human life have any significance at all? Or is meaning something we create for ourselves, a way of finding purpose in a seemingly indifferent cosmos? The cosmic background radiation doesn't provide answers, but it does invite us to wrestle with these questions, to find our own sense of meaning in the face of the infinite. Another philosophical theme that emerges from the cosmic background radiation is the nature of time. This ancient light is a kind of time capsule, allowing us to peer back billions of years into the past. It challenges us to think about time not just as a linear progression, but as a dimension that connects us to the very origins of the universe. What does it mean to exist in a universe that has a beginning and possibly an end? How do we reconcile our fleeting lives with the vast stretches of cosmic time? These are questions that touch on the very essence of what it means to be human. Finally, the cosmic background radiation invites us to consider the limits of human knowledge. Despite all our scientific advancements, there are still mysteries that elude us. The patterns and fluctuations in this ancient light hint at the early moments of the universe, but they also remind us of how much we don't know, what lies beyond the observable universe. Are there other universes, other realities that we can't even imagine? These questions push us to the edges of our understanding, challenging us to remain curious and humble in the face of the unknown. As we reflect on these philosophical implications, it's clear that the cosmic background radiation is more than just a scientific discovery. It's a gateway to deeper questions about existence, meaning, and our place in the cosmos. Next, we'll explore how this ancient light inspires us to search for meaning, not just in the stars, but in our own lives. As we continue to unravel the mysteries of the cosmic background radiation, it becomes more than just a scientific phenomenon. It becomes a source of inspiration. This ancient light, a relic of the universe's infancy, has a unique way of sparking curiosity and wonder in all who encounter it. It's not just a tool for understanding the cosmos. It's a mirror that reflects our deepest questions about existence and our place within it. The cosmic background radiation invites us to look beyond the everyday and consider the bigger picture. When we gaze at this faint glow, we're not just seeing light, we're seeing the echoes of the universe's birth. It's a reminder that we are part of something far greater than ourselves, a vast and intricate tapestry of space and time. This realization can be both humbling and empowering, urging us to seek meaning not just in our individual lives, but in the grand story of the cosmos itself. For many, the cosmic background radiation serves as a bridge between science and spirituality. It doesn't provide answers to life's biggest questions, but it does offer a framework for exploring them. Why are we here? What is our purpose? These are questions that have been asked for millennia, and the cosmic microwave background gives us a new lens through which to view them. It encourages us to think about the universe not just as a collection of stars and galaxies, but as a living, evolving entity of which we are an integral part. This ancient light also reminds us of the power of curiosity. The fact that we can detect and study something as subtle as the cosmic background radiation is a testament to human ingenuity and our relentless desire to understand the world around us. It's a reminder that the search for meaning is not just about finding answers, it's about asking the right questions. And in the case of the cosmic background radiation, those questions lead us to the very edges of our understanding, challenging us to think bigger and dream bolder. At the same time, the cosmic background radiation offers a sense of connection. It shows us that we are made of the same elements that form the stars and galaxies, that we are part of a cosmic story that began billions of years ago. This connection can be a source of comfort and inspiration, reminding us that we are not alone in the universe. We are part of a vast, interconnected web of existence, and that realization can give us a sense of purpose and belonging. Ultimately, the cosmic background radiation is more than just a scientific discovery. It's a call to explore, to wonder, and to seek meaning in the cosmos. It challenges us to look beyond the mundane and embrace the extraordinary, to find beauty and significance in the vastness of space and time. And as we continue to study this ancient light, we are reminded that the search for meaning is not just a scientific endeavor, it's a deeply human one. Next, we'll take a moment to reflect on what the cosmic background radiation means for us as individuals and how it connects to our everyday lives. Now, let's take a step back and consider what the cosmic background radiation means for us in our daily lives. It's easy to think of this ancient light as something distant and abstract, something that only scientists in labs or observatories care about. But the truth is, the story of the cosmic background radiation is deeply personal. It's a story about where we come from, how we fit into the universe, and what it means to be part of something so much larger than ourselves. Think about it this way. Every time you step outside on a clear night and look up at the stars, you're seeing the same light that has traveled across the cosmos for billions of years. The cosmic background radiation is like a whisper from the very beginning of time, a reminder that the universe has been evolving and expanding long before we existed. It's a humbling thought, but also an inspiring one. It reminds us that we are part of a grand, ongoing story, a story that began with the Big Bang and continues to unfold with every passing moment. For many of us, the cosmic background radiation can also serve as a source of perspective. In our busy lives, it's easy to get caught up in the small details, the deadlines, the chores, the daily stresses that seem so important in the moment. But when we take a moment to reflect on the vastness of the universe and the incredible journey that has brought us here, those everyday worries can feel a little smaller. It's not about dismissing our problems, but about seeing them in the context of something much bigger. It's about finding a sense of balance and peace in the knowledge that we are part of a universe that is both ancient and ever-changing. This ancient light also invites us to embrace curiosity and wonder in our own lives. Just as scientists have spent decades studying the cosmic background radiation to unlock the secrets of the universe, we too can approach our own challenges and questions with a sense of exploration. Whether it's learning something new, pursuing a passion, or simply taking the time to appreciate the beauty of the world around us, the cosmic background radiation reminds us that there is always more to discover. It encourages us to keep asking questions, to keep seeking answers, and to never lose sight of the wonder that comes with being alive in such a vast and mysterious universe. And finally, the cosmic background radiation connects us to each other. It's a reminder that we are all made of the same stardust, all part of the same cosmic journey. No matter where we come from or what our lives look like, we share this incredible connection to the universe and to each other. In a world that can sometimes feel divided, this shared heritage is a powerful reminder of our common humanity. It's a call to look beyond our differences and recognize the unity that binds us all together. So, the next time you find yourself feeling overwhelmed or disconnected, take a moment to think about the cosmic background radiation. Let it remind you of the bigger picture, of the beauty and mystery of the universe, and of the incredible journey that has brought us all here. It's not just a scientific discovery, it's a source of inspiration, a call to wonder, and a reminder that we are all part of something truly extraordinary. Now, let's shift our perspective and think of the cosmic background radiation as something truly extraordinary, a time machine. This ancient light isn't just a relic of the Big Bang, it's a window into the past, allowing us to peer back billions of years to the very dawn of the universe. Imagine holding a photograph of yourself as a baby. That image captures a moment frozen in time, a snapshot of who you were at the very beginning. In a similar way, the cosmic background radiation is like a cosmic baby picture, showing us the universe in its infancy, just 380,000 years after the Big Bang. When we observe this radiation, we're not just looking at light, we're looking at history. The photons that make up the cosmic background radiation have been traveling through space for over 13 billion years, carrying with them the story of the universe's earliest moments. By studying this light, scientists can piece together what the universe was like when it was young, hot, dense, and filled with a searing glow. It's as if we've been handed a time capsule, one that reveals the conditions and structures that would eventually give rise to galaxies, stars, and planets like our own. What makes this even more remarkable is the precision with which we can study this ancient light. Modern telescopes and satellites, like the Planck mission, have mapped the cosmic background radiation in incredible detail, revealing tiny fluctuations in temperature and density. These fluctuations are like cosmic fingerprints, the imprints of the seeds that would grow into the vast structures we see in the universe today. By analyzing these patterns, we can trace the universe's evolution from its fiery beginnings to the complex, sprawling cosmos we inhabit now. But the cosmic background radiation doesn't just tell us about the past, it also helps us understand the present and even predict the future. The way this light has traveled and interacted with the universe over billions of years provides clues about the nature of dark matter, dark energy, and the overall geometry of the cosmos. It's like having a cosmic roadmap, one that guides us through the universe's history and points us toward the mysteries that still lie ahead. So, the next time you hear about the cosmic background radiation, think of it as more than just a scientific curiosity. It's a time machine, a tool that allows us to journey back to the universe's earliest moments and witness the birth of everything we know. It's a reminder that the universe has a story, and we are part of it. A story that began with a single, explosive moment and continues to unfold with every passing second. And as we continue to study this ancient light, we're not just looking back in time, we're also looking forward toward the endless possibilities that the universe holds. As we look ahead, the cosmic background radiation continues to hold the promise of unlocking even more secrets about the universe. Imagine a future where our technology has advanced to the point where we can detect even fainter whispers of this ancient light, revealing details about the cosmos that we can barely fathom today. The next generation of telescopes and space missions, equipped with unprecedented sensitivity, might uncover patterns or anomalies in the cosmic background radiation that could challenge our current understanding of physics. What if these discoveries lead us to new theories about the fundamental forces of nature, or even the existence of dimensions beyond our own? One exciting possibility is that future observations of the cosmic background radiation could provide definitive evidence for cosmic inflation, the rapid expansion of the universe in its earliest moments. If scientists can detect specific signatures, such as B-mode polarization, it would not only confirm inflation, but also offer clues about the energy scales at which it occurred. This could bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that have yet to be fully unified. Such a breakthrough would reshape our understanding of the universe's birth and its underlying laws. Another area where the cosmic background radiation could revolutionize cosmology is in the study of dark matter and dark energy. These mysterious components make up the vast majority of the universe, yet we know very little about them. Future measurements of the cosmic background radiation might reveal subtle interactions between dark matter and ordinary matter, or provide new insights into how dark energy drives the accelerating expansion of the universe. These discoveries could fundamentally alter our view of the cosmos, answering questions that have puzzled scientists for decades. Beyond these scientific advancements, the cosmic background radiation could also inspire new ways of thinking about our place in the universe. As we uncover more about its origins and evolution, we might gain a deeper appreciation for the interconnectedness of all things. The story of the universe, as told by this ancient light, reminds us that we are part of something much larger, a cosmic tapestry woven over billions of years. And as we continue to explore its mysteries, we are not just observers, we are active participants in the ongoing journey of discovery. So, as we stand on the brink of new cosmological frontiers, the cosmic background radiation remains a beacon, guiding us toward a future filled with wonder and possibility. Each new discovery brings us closer to understanding the universe's deepest secrets, and with every step forward, we are reminded that the cosmos is a place of endless exploration and infinite potential. The journey is far from over, and the best may be yet to come. As we bring our cosmic journey to a close, let's take a moment to reflect on the profound significance of the cosmic background radiation. This faint glow, a relic of the Big Bang, serves as a time capsule, preserving the story of the universe's earliest moments. It is not just a scientific curiosity, but a cornerstone of modern cosmology, offering us a glimpse into the birth of everything we know. From its accidental discovery by Penzias and Wilson to the groundbreaking missions like COBE and Planck, the cosmic background radiation has reshaped our understanding of the cosmos, revealing the universe's age, composition, and even its ultimate fate. Through this ancient light, we've uncovered the seeds of galaxies, the fingerprints of dark matter and dark energy, and the echoes of cosmic inflation. It has challenged us to rethink the very fabric of reality, pushing the boundaries of physics and philosophy alike. The cosmic background radiation reminds us that the universe is not static, but a dynamic, ever-evolving entity, filled with mysteries waiting to be unraveled. It connects us to the past, grounding us in the story of our origins, while also pointing us toward the future, where new discoveries await. So, as we conclude this exploration, let's carry forward the sense of wonder and curiosity that the cosmic background radiation inspires. The universe is vast, complex, and full of secrets, and each discovery brings us closer to understanding our place within it. What other mysteries lie hidden in the faint whispers of this ancient light? What new questions will arise as we continue to probe the cosmos? The answers are out there, waiting for us to find them. If you've enjoyed this journey through the secrets of the cosmic background radiation, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the wonders of the universe. And as you go about your day, take a moment to look up at the night sky and ponder the incredible story written in the stars. The universe is calling. What will you discover next? you.